Hello, my name is Jack Holland, and today I'll be presenting our presentation to the marketing department regarding our new advancements on utilizing a neural network classifier for textual data. So, for some introduction and background, I'm part of the business analytics team, and we are in a highly competitive industry. And part of our responsibilities is the task of monitoring the corporate communications of one of our or many of our key competitors, and we're looking to determine the category of information being communicated. In order to complete this, a data file has been made available to us that includes sample messages previously communicated from our competitors. In this process, we're looking to determine the category of the messages, and so we will be applying the attached corporate messages Excel file that's used to um, train and test the model for our task. The text field provides communicated information, and the category field um, includes the specific category of each message. Categories we're looking to identify fall into three fields, which are information, dialogue, and action. Once our model is developed, it will be used to make predictions on where these messages follow, which can help generate some useful insights for our organization. So, to begin our presentation, we're going to go over the flow of our code and just show the process of model development, model testing and training, as well as the um, performance indicators that are generated through our testing processes. So here we have our entire code um, laid out in our Jupyter Notebook file. We're using Python for the coding process of our model. And then after running, we can observe all of the outputs generated. And so to begin, our first step is to disable all warnings. This will allow for just the smoother um, construction and testing of our model and of our code. After this, we're going to look to install and import all of the required packages to our working environment. In this process, we'll be using Pandas, Matplot library, PyPlot, Seaborn, and the OS software. After this, of course, we're going to set up our working directory. For this task, we'll be working out of the downloads folder of our computer, and then we'll print our working directory to ensure that we're working out of the right folder. Once this is confirmed, we're going to look to import the records from the corporate messages Excel file that was attached through the prompt for this task. So we're going to set our file path and then create a data frame that reads the Excel file path. After this is done, we can print to make sure that our data frame was successfully created. In this new data frame, we'll go ahead and convert the string labels into numbers for the category field. So we will import pre-processing from sklearn, and our code here provides the process that's undergone to convert each of the string labels into numbers. And we can print to confirm that this is done correctly. Moving forward, we're going to go ahead and partition X and Y into training and testing sets, with 80% being training and 20% being testing. So we'll import our train test split. X is going to be our category, and or X will be our columns, and Y will be our category. We'll use our code for the testing and training splits, and we'll print to see our outcomes. It's now time to create our initial MLP neural network classifier and build our model. So we'll import the MLPC class or the MLP classifier from sklearn, and then we'll set our parameters and write our code to create this model. Upon completing this step, we will go ahead and train our model and predict responses, and then determine the accuracy of our initial model. So we will import our accuracy score. We'll fit the model and then test our predictions. Our accuracy is going to be the accuracy score function for our y test and our y predictions. And we'll print our accuracy score, and then we'll test this to see if we can improve it by the processes of our next step. And our next step will be to update the MLP network classifier and rebuild our model, adjusting our key parameters as we go. And so we can see code written with adjusted parameters that we will go over. This is going to give us an improved accuracy score that we will print to confirm. After we've improved our model, we're going to go ahead and create our confusion matrix for the model with our confusion matrix function from sklearn metrics. Our confusion matrix will include our y test and our y predictions. The heat map function will allow us to assess each of the categories as well as, well, the predicted categories as well as our actual. Additionally, we'll create more visualizations related to model performance, and these will further reveal the overall accuracy and just overall performance of our model. Lastly, we would like to calculate comprehensive metrics for the model. Our accuracy score, our F1 scores, our precision score, and our recall scores, along with our Matthews correlation coefficient, will all be great indicators of how well the model performs with our sample data. Once we input our sample data, we'll have phrases that would be commonly found through the communications, and our model should be able to successfully determine whether these are um, either of the three text forms. With our data frame predictions, we can assess the overall performance of our model. So, as we were creating our model, we underwent the process of adjusting our classifier settings. In our initial model, we had 100 neurons. We used the ReLU activation, the Atom solver, and a learning rate of 0.001. Upon adjusting the model, we found that using hidden layers of 200, 150, and 100 neurons, as well as the 10H activation, LBFGS solver, and a learning rate of 0.005, increase our model accuracy from 0.7906 to an improved accuracy score of 0.8372. So we can see that refinements were needed, and they were made through the process of adjusting parameters until improved performance was observed. We have our model accuracy scores from the initial model and the improved score that was found through modifying the model for new accuracy. We also discuss the addition of a confusion matrix that is used to reveal predicted outcomes compared to actual outcomes. To gauge the results of the model when faced with testing and training data, this confusion matrix was created to reveal all results when classified. As we can see, this demonstrates that most prediction results were consistent with actual classes, and there weren't many false classifications in each category. We can see that for the action category, 7 were predicted correctly, with 3 incorrect or false predictions. The model was perfect in predicting um, the dialogue category with 0 false predictions. The information had the most correct predictions, along with 4 false predictions. So, while there is room for improvement, the overall results of the model were quite promising. With this in mind, we can move forward to our model results, where we observed an accuracy score of 0.8372, a precision score of 0.8298, a recall score of 0.8191, and a Matthews correlation coefficient of 0.7521. Um, all of these scores recorded are able to demonstrate the effectiveness of the model when it comes to predicting textual data. Um, all of these scores contribute to the conclusion that the model is able to effectively identify text at a high rate while also keeping false negatives at a low rate. These abilities signify an effective model that can consistently identify text data and classify accordingly. Our, lastly, our Matthews correlation coefficient confirms the success of this model in text classification. Um, moving forward from our accuracy scores, we've also generated plots that are created to demonstrate the effectiveness of the model. 2 plots out of the many that were created included the lift plot and the cumulative gains plot. The lift plot reveals additional performance that is acquired from using the predictive model instead of a random model, and the cumulative gains plot visualizes model's performance in successfully predicting text classes versus other plots. And then, as you can see through the visuals, both of these revealed that the model was very successful and it provided much value over other model options. As we start to wrap up our presentation, we can see through our results that um, predictions were consistently accurate and they were as expected, as this was the intention of creating the model in the first place. Um, we can see that text data from competitors is properly classified into correct groups of information, dialogue, and action. In order to create these predictions, we're using the digits of 0 regarding information. 1 correlates with dialogue, and 2 is for action. To conclude, our model is able to effectively identify text at a high rate with low levels of false negatives and false positives, and overall, our classifications are accurate and consistent. With the success of this model in mind, it's important to consider some limitations of the model. And so, while it's clear that the model works very well with training tests and sample text data, it is to be seen how the model performs with more complex text. Observations must be made when the model is faced with more complex text data, um, in which cases will be more difficult to predict. And so it will take time and application of the model to officially gauge the success of the model. Some suggestions for improvement include, of course, that improvement will come with application of real-world data. And we understand that tweaks can be made to parameters to improve accuracy as it was through the training modifications. This does not necessarily mean that the model will need improvements, as improvements may or may not be necessary, but this should be heavily monitored in the case that it is required. Lastly, our recommendations to the organization. Um, with the confirmation of performance metrics, accuracy scores, and plots of model performance, the organization should be quite confident in the model's ability to determine the category of communicated information. While consistent, accurate predictions can be made with the training, test, and sample text data, observations should be made when the model is faced with complex real-world data. In these cases, predictions may be more difficult, so additional tuning can always be done.